Hi everyone, welcome. My name is Omar Sanseviero. I am a ML engineer at Hugging Face, and I'm very excited to be hosting this event. Today we are welcoming the DietNeRF team from the JAX Flax event that we held a couple of months ago. So you will hear all about it in a couple of minutes, so I won't say much. But this team was able to implement DietNeRF in JAX, which is a very nice model that is able to reconstruct 3D scenes with just a couple of views. So that means that from a couple of images from different angles, they are able to reconstruct a 3D scene. So it's super interesting. As a reminder, you can join in Twitch, YouTube, and LinkedIn. We also welcome you to our Discord server, to the general event chat room channel, and ask questions there as well. So I will be keeping an eye there if people have any questions. And if you don't know what's the link to Discord, you can see below in the banner. So let me introduce the speakers for this talk. We have Stella Young. She is a PhD candidate at the Seoul National University. She does research about NeRF, scene generation, 3D vision, and visual localization. So welcome. We also have Sunjung Lee. He's a PhD candidate at the Hinha University. His research areas are computer vision, machine learning, and neural network light weighting. And finally, there's also Alex Lowe. He currently works at the AI software as an AI software engineer in Pencil in Singapore. So having said that, please let's give a virtual applause to the speakers. And thanks a lot for joining. I leave you up to it. Welcome.
Yeah, thank you for a nice introduction for Omar. And let's start our presentation. Hello, everyone. Thank you for coming our Hugging Face talk. My name is Soyeon Yang, and this is our team who will present today. Yes, we will introduce our implementation of DietNeRF with JAX and Flax. Today's presentation agenda is follows. For computer vision field, the 3D vision is new rising field in these days. You can find the tremendous papers are coming on the many conferences, and this graph shows the 3D is one of the hot topic for the computer vision research. The reason why the computer vision is popular is maybe it have many application industry field which is growing fastly. Among 3D vision, there are some new syndrome of the nerve. After the vanilla nerve paper is coming, a lot of nerve variant papers are submitted. This speed beyond the pace of Gian's popularity, and almost 534 paper use this nerve paper. If we look for the cause of this syndrome, I think it has to do with the recent metaverse trend. In the metaverse, the law of creating 3D objects, creating avatars, and generating scenes will become very important. So these future prospects increase the interest of the nerve and occur the explosion of the nerve research. Now, let's look at the structure of nerve one by one. NeRF is actually just a multi-layer perceptron which can encode the scene's radiance field. The input of the NeRF is the 3D coordinate pose, which is the 3D location and 2D viewing directions. Also, the output is emitted color and volume density. The training process is follows. At first, we sampled the 5D coordinate among camera rays, and next, feeding those locations into an MLP to produce a color and volume density. After that, using volume rendering techniques to compose these values into an image. This rendering function is differentiable, so finally we can optimize our scene representation by minimizing the residual between synthesized and ground truth observed image. The NeRF rendered the color of any lay passing through the scene using principles from classical volume rendering. To explain the volume rendering process, you can check this integral formula. The function T denotes the accumulated transmittance along the lay from Tn to Tf. The Tn and Tf is the lay's near and far bound, the limits of integral. The volume density delta can be interpreted as the differential probability of a lay terminating at an infinitesimal particle at location r. The term C means the total radiance light that the point at T of R sends in the direction D. NeRF numerically estimate this continuous integral using quadrature. Deterministic quadrature, which is typically used for rendering discretized volume voxel grid, would effectively limit our representation's resolutions, because the MLP would only be queried at a fixed discrete set of locations. It used a stratified sampling approach where we partitioned Tn to Tf into n evenly spaced bins and then draw one sample uniformly at random from within each bin and use these samples to estimate C color with the quadrature rule. Usually, deep learning networks are biased toward learning lower frequency functions, so the mapping the input to a higher dimensional space using higher frequency function before passing them to the network enable better fitting of data that contains high frequency variance. Gamma is a mapping function from R into a high dimensional space, R power to L, which is not trainable. It is just a position encoding function and given some hyperparameter. This is also can be found on the famous model transformer architecture. Our rendering strategy at every end query point along each camera lay is inefficient. So to optimize a neural radiance field, NeRF use some hierarchical volume sampling. In first core space, NeRF samples a small number of points and C using the naive stratified sampling. This path will tell us the region where good point lies. In the second fine path, we will treat normalized weight. This normalized weight produces a piecewise constant PDF along the lay. Evaluate our fine network at the union of the first and second set of samples and compute the final rendered color of the lay C. Yeah, the NeRF structure was suggested, and the result is shown here. To evaluate NeRF model, the author compare against current top performing techniques for view synthesis. NeRF can be able to recover fine details in both geometry and appearance. You can check this result video quality.
Oh, it's not playable.
Yeah, you can check it in the NeRF official page. So if you're interested in, please visit. Yeah, after the binaural nerve, there are many variants of nerve is coming. Even if it's nice quality, the inference was not real-time speed. So there is some work to deal this problem. Plain oak trees use the oak tree structure to speed up the geometry query, and baking neural fields use a slightly different data structure to save the explicit geometry. At last, a killer nerve proposes the decompose this large deep network into a set of small shallow networks that captures only a small portion of the space and make a much faster network. Moreover, the nerve has a limitation as a slow training speed. So it needs too much training time for only one scene. Some work attempt to find a general nerve that can quickly transfer to all scenes. For example, the pixel nerve introducing an architecture that conditions a nerve on image input in a fully convolutional manner. This allows the network to be trained across multiple scenes to learn a scene prior. Also, MVS nerve using some multi-view geometry knowledge and used cost-volume concept. Also, our project DietNeRF used semantic consistency loss using 2D to 3D supervision as a prior knowledge. At last, some meta-learning approach is done and finding some generalizable initial weight for nerve. Besides, some effort focus on dynamic and articulated scene. NeRF deforms video using a second MRP, applying a deformation for each frame of video. Animatable nerve use a tracked skeleton from mocap data and multi-view video to train skeleton-based blend fields that then transform the Radian sphere, enabling skeleton-driven synthesis of people's avatar. Because the nerve needs some position level and camera intrinsic parameters. So like iNerve and self-calibration nerve, they try to find that camera information. Also, there are further attempts such as IMAP, which apply it to SLAM. Some nerve variants try to decompose the nerve geometry, appearance, and position transformation components in the scene. Giraffe and Giraffe and Edit Nerve show this decompositional control is possible in nerve scan. At last example, several research was conducted to create a more natural synthesis scene view with nerve. Gancraft transforms the Minecraft block structure into realist scenes, and StyleNerve synthesizes a very natural 3D face from multiple angles. Yeah, this is introduction of nerve variants, and
As Stella explained, NeRF is a very powerful tool to render the 3D object, but it still has a limitation. Then NeRF often fails to synthesize an overview when trained on limited data. Here, with 100 views, NeRF will synthesize hot dog in every viewpoint. It looks clear, and there are no standing out artifacts. However, with 8 views, the object is jittered, and in some cases, NeRF completely fails to render. To solve this problem, DietNeRF is proposed. The name is a diet of the training dataset. In a nutshell, to reduce the quantity of the training dataset, DietNeRF injects semantic consistency constraints, making a hot dog look like a hot dog in every direction. Before discussing DietNeRF, let me first explain the reason why NeRF has this problem. The authors of DietNeRF argue that NeRF has these three problems. all fitting, regularization, and no prior knowledge. First, the NeRF is very easy to overfit. NeRF is trained to estimate RGB value from corresponding rays. At this time, there are no special constraints, and if the dataset is limited, NeRF is easily overfitted to the same pose. When NeRF overfits to training pose, it cannot be generalized to the unseen area, that is, an area that no camera has seen. As shown in this figure, when only the right side of the Lego is visible, the left area is not rendered at all. It is because this region has not been trained, and it almost depends on random initialization. The most intuitive and widely known way to solve overfitting is to reduce the network capacity and apply regularization. Accordingly, the authors applied the following regularization tricks to see whether the problem is resolved or not. You can see that simplified NeRF has a clear performance improvement in the unseen area. However, the artifacts are still severe, and in the seen area, the performance is degraded. In other words, simple regularization cannot completely solve the overfitting problem of NeRF. The authors argue that this problem is caused by a lack of prior knowledge. NeRF is running without any semantic information, which means that NeRF renders objects without understanding what it is. Therefore, to make NeRF generalized to unseen views, the authors thought that the semantic information should be injected as the prior knowledge. The authors proposed DietNeRF that injects semantic information to NeRF. By applying constraints to ensure high semantic consistency, DietNeRF can render unseen views well without compromising details. The concept of DietNeRF is very simple. Semantic information of the object is extracted from the known views using a pre-trained network such as ClipVIT. Then, DietNeRF minimizes the semantic difference between the known views and the rendered views. The known views are drawn from training set, and the rendered views are randomly sampled so that they are novel. As mentioned earlier, this concept is to have the same semantic information as the seen view with any novel view. In other words, a Lego should look like a Lego in any pose. Experimental results show that DietNeRF renders unseen views well, without compromising details of seen view. It's still not perfect, but if you compare it to NeRF, you can see that there is a vast improvement.
So next, before we going through the implementation details, so we would like to give an introduction to JAX. Firstly, because we mainly implement in JAX in our model. Also, secondly, I believe some of the audience may hear a lot about JAX, but may not have some hands-on experience on it. So essentially, what is JAX? JAX is a framework designed by Google Research for high-performance numerical computing. So to me, I think JAX has three core features. Firstly, it has a NumPy-like interface. Secondly, its code can be easily accelerated on different devices, such as CPU, GPU, and TPU. And also, one key feature I would like to highlight is the composable function transformation. So actually, by the first time I look at this term, I really don't know what it is. So I would like to take this chance to take a little bit on what it is and briefly how does it work. So what is composable function transformation? Essentially, you can think of it as a transformation to transform a Python function to another Python function. The purpose is to extend its original functionality or change its functionality. For example, the phi map, p map, JIT, or grad is some of the example of function transformation that is offered by JAX framework. So it is called composable because the return of this kind of transformation is another new Python function. So with this new Python function, you can apply another round of function transformation again. So that's why it is called composable. So no matter what kind of function transformation you're going to apply, there are some common steps that is performed underneath the hood in JAX. So you may wonder by the time the user, let's say, define a function that's called log2, what is happening underneath the hood when we apply a function transformation on log2? Let's say we apply a JIT on it. JIT stands for just-in-time compilation, which I will explain later. So what is happening underneath the hood is that firstly is trying to, JAX is trying to trace the operation that is performed in this function. It is trying to wrap the function input, which is X in this case, by a tracer object. In this case, the tracer object is called shape array, sorry. So this shape array will keep track of the dimension, the shape of the input, and also the type of the input. And then the JAX will step through each line of the function in order to record each operation that is applied on this tracer input. So once you have record this kind of input, what you can do is you can reconstruct the whole function with a so-called intermediate representation. So this intermediate representation is shown on your right-hand side in purple color. So this intermediate representation is called JAXPER. Essentially, it's trying to encode the primitive operation, which is some elementary operation like logarithmic and division of this function, and try to encode that and represent it. So once you have this intermediate transformation, right, you will see that at the center, we already get a intermediate representation from the user-defined function transformation on the left-hand side. So once you have this intermediate representation, you can achieve many purposes. So what JAX doing is with this code, they will use a JAX interpreter to reinterpret this code into different purposes. For example, you can use this intermediate representation to transform it into another new Python function. We can do auto factorization, which is what VM do. On the other hand, you can also transform it in a way that it can support parallelism to run across different TPU cores. This is what PMAP is doing. On the other hand, you can also transform it in a way that it can support the first derivative. This is what grep is doing. Meanwhile, you can also apply the just-in-time compilation on it. So to give more details on it, what it is essentially doing is that by the time you wrap the function by JIT, it will reconstruct the code into something like a high-level optimized code, stand for hello. And then this high-level optimized code will serve as an input to a compiler, which is called XLA. The XLA stands for Accelerated Linear Algebra Compiler. Essentially, what it does is it's trying to interpret the whole operation of this function and then try to come up with some optimization for it to fill some of the computation, so as to speed up. And then what it will return is essentially a domain-specific compile code. This domain-specific compile code means that the code is specific to different devices, TPU, GPU, or CPU, so that the user only need to define the code on the left-hand side, and the JAX will do the rest for you. So as for Flax, it's another framework that we use. It is a deep learning framework that is built on top of JAX. So it provides a pretty nice interface for us to define the models and optimizer. So these two examples are the example for the model definition for convolutional network, and also how we define the state. Here we define the model, also need to define the weight parameters together with the optimizer. Then we will wrap this by a train state. So I believe some of the audience may wonder what is the difference between JAX and other popular deep learning frameworks such as TensorFlow and PyTorch. So from my experience, I can name a few, and they are categorized by pros and cons. So firstly, start with pros. I think that for the JAX, it can be easily run on different devices without any code change. So I would say it's pretty easy to use for different devices. Meanwhile, it's also applicable to many domains as well. So in TensorFlow and PyTorch, I believe they mainly use in probabilistic programming or deep learning. But in JAX, not only it can be applied on differentiation optimization, it can be used in some data preprocessing as well, and also used in simulation. I do see some example from Twitter. They are trying to apply the JAX in data augmentation, essentially just trying to augment the image using the TPU cores distributed nicely so that you can gain a significant speed up. So meanwhile, since it is NumPy-like interface, I believe this interface is super easy to use for most of the user who are get used to NumPy or SciPy. Also, it has a pretty flexible control on the parallelism. So it is very beneficial for you to do large-scale computing in the sense that you can nicely control in what kind of dimension, in what kind of area you want to distribute your compute across different TPU cores. So right now, JAX has a PMAP to support that. On top of that, it also have a beta features, which I recently seen in the documentation, which is called XMAP. And on the other hand, is empirically, I see that it's generally run faster than other framework. But undeniably, it also have some limitation as well. One of the major limitation from my experience is that it will give you some unexpected outcome if you are trying to apply your function transformation improperly. Essentially, if your function has some side effect, for example, you have a print statement in it, or you insert a global variable in it, the JAX cannot correctly interpret this. So as a result, you will get out some unexpected outcome without any warning. So this is something you need to pay attention. On the other hand, I would say JAX is a pretty new language. So I would say it takes some time to build up the whole ecosystem. I mean, it's associated high-level frameworks. So here is just some screenshots showing the performance of JAX comparing TensorFlow and PyTorch. And you can see that in general, in some case, for example, in Transformer and also ResNet, it is training faster than other frameworks. So finally, if you want to know more JAX and Flax, we do have some resources attached here. We have some YouTube talk. Particularly, I will highlight the second one. Essentially, it's a talk held by Jake van der Plas. He's a Google developer who is developing JAX. He gave a really nice introduction to JAX. And also, you can feel free go into the JAX and Flax documentation. Also, we also have a study. I also noticed there's a study group organized by Weights and Bias. Sam Bhutani will walk us through the JAX. We'll study the JAX together with the audience. So it just organized recently. So I would highly recommend to join this if you want to know more about JAX.
Okay, now I will explain how we have implemented DietNeRF. But first, you should note that our implementation is not exactly the same because of some unspecified hyperparameters and lack of our JAX skill. Nevertheless, our implementation seems to work quite well and can reproduce most of the results the authors have reported in the paper. Therefore, if you have enough JAX skill, you can get better results based on our implementation. There are three core parts for implementing deep learning algorithms: data provider, network, and objective function. The overall algorithm is shown here. Marked lines indicate DietNeRF things and others indicate NeRF things. As I said, it looks straightforward. Prepare semantic information using same view, render image from the random pose. Extract semantic information and minimize the difference with information from same view. Here, since the network is the same as NeRF, our main task only was to implement the other two parts, data provider and objective function. It sounds easy, so we underestimate that these are not very difficult tasks, but they were not because of some problems. Let me explain them step by step. The first part is the data provider. Fortunately, the pre-trained Cliff VIT model is already in the Flax library. Also, it is very much easy to use. One line is enough to load it. The only thing we had to do was implement a pre-processing algorithm for Cliff VIT by the JAX library. This pre-processing is well-known ImageNet normalization. And here, we can specify the data type of Cliff VIT. As will be explained later, we need to reduce the memory cost of DietNeRF parts. Half precision is utilized to Cliff VIT, therefore. One more important thing that I want to inform you is this code looks like a NumPy code. If you replace JMP into MP, most of code will work well, except for JAX image resize. There is TF image resize in TensorFlow. In JAX, There are so many TensorFlow-like things, such as JAX-con, JAX-while loop, and JAX-slice. To me, JAX language looks like a combination of NumPy and TensorFlow. You know that JAX is developed by Google as well. So if you are a TensorFlow user, you can learn JAX quite well. Back to the data provider, the next step is generating the random pose. A random pose can be easily implemented by picking one pose as the default and implementing other pose as its rotation. The realistic synthetic dataset we used in this project deals with the upper hemisphere. Therefore, our pose boundary is expressed as shown in this figure. If you know about spherical coordinates, this representation might look a bit weird. In general spherical coordinates, phi does not go from bottom to top, but from top to bottom, which means the North Pole is 0 degree. However, we thought that this might seem rather strange to demo users, so to make it user-friendly, we reversed the phi coordinates and set the front view as the default, that means 0 degree. As a result, theta has a boundary from minus pi to pi, and phi has a boundary from 0 to pi over 2. For radius, the dataset boundary was used as it is. Unlike most of the code used here, you are probably not familiar with JAX random split. JAX random split is a function that generates a random seed. It receives RNG and returns RNG again and RNG input, which is a random seed. Therefore, if only the first random seed is determined, we can easily generate a sequence of random variables to perform pseudo random number generation. Since random seed control is one of the important parts of reproducing, it is quite beneficial to support these functions natively. The next step is to generate rays according to a random pose. In the realistic synthetic dataset, image resolution is 800 by 800, and it is usually sampled to be 400 by 400. Both are too large and will consume too much GPU memory, so the authors utilized three tricks to reduce cost. The first is coarse sampling. The authors reported that they used a large sampling stride and used only about 15% of the number of rays. It's kind of weird why the authors didn't mention the specific stride, but they would have used a stride greater than 2 anyway, and fewer rays than 400 by 400. The second is mixed precision. The authors use single precision for NeRF and half precision for running semantic information. Then, the additional memory cost can be reduced by half through, and it can be applied easily by denoting the data type of race and network. The last is deleting and limit realizing activation. This trick keeps as many tensors as needed on the GPU, and the rest detached, which makes the number of tensors on the GPU minimized. However, JAX doesn't natively support it. JAX focuses on static mode for JIT compiling, which is not available on this kind of trick. Even though we dropped the JIT compiling, it would be quite tough to implement this training process. We were almost a newbie of JAX and Flax when we started this project. So we had to skip this trick, but the problem was that the memory cost increased dramatically. Since the network could not be changed, we had to find a way to reduce the memory cost further while still delivering semantic information. We first checked the maximum number of arrays that could be loaded to our hardware, and it was 75 by 75. This was less than 1% of the original arrays. If we use this resolution, NeRF can see the shape of the object, but cannot know the fine details at all. This figure is a Lego bulldozer sampled at 75 by 75 size. A bulldozer is recognizable, but details like a Lego bump are barely seen. In order to solve this problem, we first reduced the image size through the random crop. Then, we set the sampling rate to 4 to get as many rays as our GPU can handle. As described before, our data provider samples various radiuses. So, with the new sampling strategy, some images show the overall shape as shown in this figure, and some others show fine details as shown in this figure as well. Therefore, we expected that the performance improvement achieved by DietNeRF would be reproduced with this scheme. Surely, it would be better to use arrays, but most of the experimental results confirm that our DietNeRF has higher performance than NeRF. The implemented code is shown on the right. The first thing I want to note that is the tree map. Tree map applies the given function to the leaves in the nested list. It's not very special, but it makes coding easier and clearer. And the chart distributes the data as many as number of GPUs for distributed running. It simply has the form of NumPy reshape, and it is implemented through streammap as well. Finally, data for running random pools is prepared by specifying the data type as half precision. Next, I will explain the training step for running semantic consistency. Earlier, I said that this process was just formed by NeRF. It was nearly true. However, during the implementation, we discovered that the code for single and multi-GPUs had to be different. Accordingly, we first separate the training step of NeRF and the semantic consistency training step. And following the lazy regularization concept, which is often used in GAN, semantic constraints are delivered at regular intervals. On the green line, the data provider prepares the training data and decides which training step to use based on the number of devices in the green box. First, I will explain the single GPU version. Because NeRF uses two-dimensional matrix, that is, batch arrays, we reshape the arrays first and apply it to the model to render the image. Next, convert the rendered image back to a three-dimensional tensor and put it into clip to get embedded features. Finally, DietNeRF is trained to minimize the difference with the embedded feature of the scene view. The semantic loss function is put value and grad, and the gradient is calculated. The training variables of NeRF are denoted on the blue line, and their gradients are computed by autograd. This process should be familiar to TensorFlow 2 users. This is because this area operates in almost the same concept as the gradient tape. Even if you are a PyTorch user, I think this structure is not difficult to understand. But the problem occurred when we expanded this training loop to multi-GPU. As shown in this figure, when multiple GPUs are used, rays are distributed to each GPU. If the model we run is typical NeRF, the implementation is finished here, and the training loop runs without any problems. However, we cannot put distributed images in clip. In other words, distributed images should be put into clip after combining them to become one whole image again. I'm not a PyTorch user, so I don't know the case in PyTorch, but TensorFlow requires a lot of code to implement this kind of flexible communication between GPUs. However, JAX makes this process relatively easy. Now, NeRF and clip are defined through different functions because they operate in different GPU environments. The rendering function applies pmap like the existing training step. Pmap makes the input function works on multiple GPUs, multiple devices, as Alex explained. On the other hand, as mentioned earlier, images for clips should not be distributed. Therefore, you can see that the IG values obtained through the render function is unsharded and allocated on one GPU. Unshard is not a special function. It simply makes two images into one using tensor reshape. In other words, communication between GPUs in JAX is very flexible and can be implemented more easily than TensorFlow or PyTorch. Yeah, that's it for our implementation of DietNeRF. There are some imperfect parts, but it was great opportunity to practice on JAX. In particular, as you can see on previous page, you can see the advantage of JAX over TensorFlow and PyTorch.
Yeah, Seungyeon explained our implementation well. And next, I want to introduce the story of our sprint journey. Yeah, it is a funny story. Yeah, our first journey began when I found the Hugging Face JAX Flax sprint post on Facebook. At the time, I desired to study about the JAX because JAX is famously used on NeRF to increase the performance. So I thought this contest is a really good opportunity. After talking with my friend Jaeyoung, we make a team and we like the proposal for DietNeRF. There were many natural language teams, but I suggest the DietNeRF because it used the creep model. Team began to recruit it on the bulletin board, and finally, the global team is composed with 10 people. Our team is consist of 5 South Korean, 1 Hong Kongian, 2 Indian, 1 Bangladeshi. Yeah, communication with many country people was really hard, and we need to find some efficient communication strategy. So we created a Notion dashboard and specifically divide the team as NeRF team, creep team, and crowd team. We allocate our work equally and efficiently to these 3 teams. Also, I tried to clarify the Git branch name and create some GitHub issue to deal the multiple errors. Moreover, Hugging Face and Google Crowd give us a useful talk about JAX Flax and transformers. So we could learn a lot about JAX grammars and useful tools and some platforms like Space and Hugging Face Hub, etc. And 1DB support us. Also, our mentor Patrick and Surat and many organizer give some good operation, and they especially our mentor Surat give us some code review, and it becomes a great help. Luckily, we become the top 15. Our Hugging Face mentors gave us a very detailed review report, and with this feedback, we raced for the final top 3. From that day on, we stayed up all night with coding because of our lack of research. Our team bought many Collab Pros account for this competition. In my case, I bought 4 Collab Pro account for this competition and spent a lot of money. But it is okay. Yeah. At such a difficult moment, I asked it in the Facebook post, is there anyone who could lend me a more Collab Pro account? So at the post, Min Hyun, who is the CEO of Common Computer Company, he want to sponsor us. Yeah, so he lent a full V100 GPU unit for us. It was like meeting an angel for us. Thank you so much, Common Computer. Finally, we make it into the top 3. I was really proud and happy for this competition. Thank you for our nice team who work hard day and night. And I think it's because we did a great job of visualizing our results on space and some blog posts. Alex like a nice blog post with Hassan. Yeah. Also, when we post this winning news on our Twitter, the author of DietNeRF, Ajay Jain, praised us with like and message. And the famous professor Peter Abil also hit the like button. I am really a fan for him. Yeah, especially Omar tagged us in Twitter post. Some people related to NeRF, and it was really helpful. So thank you so much, Omar. Yeah.
So finally, we would like to cherry pick some of the experimental results. So the first set result is that we are trying to train the Lego scene and also the ship scene on 14 samples. But these 14 samples are biased on one side only. As you can see, the Lego only shown on one side, and the ship is also only shown on one side. So what we get at the end, if you look at right-hand side for the NeRF, if it is trained on such a biased samples, what you'll end up is that on the side that is unseen in the training set, it looks pretty blurry, and you will see some artifact in the background, and it is pretty severe if you look at the ship scene. But on the other hand, if we use DietNeRF, on the other hand, what you'll get is that it can nicely render another side thanks to the prior knowledge injected by the pre-trained model like Clip. So here we can show that our implementation is working. So lastly, we would like to showcase our demo shortly. And this demo is hosted by Hugging Face Spaces. It's the latest platform released by Hugging Face. Essentially, the purpose is to make the machine learning deployment very easy. With this platform, you don't need to maintain your own server. You don't need to write any Docker container. And what you need to do is just to open up a repository in this Hugging Face Spaces, and then you can keep pushing your code, and then they will do the version control for you. Also, it supports automatic deployment, which means that you only need to have your package installation file. Also need to write your file for firing your application, your app. And then once you push the code, they will do the automatic deployment for you. So for time being, I already navigate to our demo. So as you can see on the right-hand side is the rendering result by DietNeRF. Right now, what you can see is the scene. This is the microphone scene. And it is trained on 8 training samples by DietNeRF. And on the left-hand side, you can control the viewing pose. For example, for the first lighting bar, you can control the rotation on horizontal axis. For example, if I want to view this microphone with some rotated anti-clockwise by some degree, wait a few minutes, then you will see the render result. So one thing to note is that luckily our platform is supported by GPU devices. So usually it takes quite a long time to render. In this case, yeah, you see, right now it is render result in only around 10 to 30 seconds. So as you can see, this is a microphone where you rotate clockwise by some degree. And yeah, since we are supported by GPU device, it runs really fast. But if you are running in CPU, it will take so much time to render, something like 1 to 2 minutes. The reason is because by the time you render, you need to ask the NeRF model to render every pixel, and it is super expensive, particularly when you want to render a full resolution image. And if you are interested in our demo, feel free to go through to our demo, play around on it. So lastly, we want to highlight one of the myths that are still unable to address. Essentially, for some experimental results, we cannot reproduce it, mainly on the setting where the DietNeRF and NeRF is trained on the examples. In the paper, we see that the NeRF really struggle on some unobserved region if you are training in such a sparse sample. But what we get is that it's not as bad as the paper state. So you see that on the bottom is the rendering result from us. Having said that, another side is looking blurry, but it's not as bad as stated in the paper. So up till now, we still cannot identify the reason yet. Maybe it's because of the compromise that we did in the implementation. I believe Xion already mentioned that. Maybe it's because of the difference between the PyTorch implementation and the JAX implementation. I believe for the paper, it is implemented in PyTorch for the NeRF and DietNeRF. Also, it may also have something to do with the hyperparameter that we choose, because the paper doesn't specify the hyperparameter. We need to choose them by experiment. They may have other factors as well, such as the weight initialization and the samples that we select. Up till now, I would say we still identify the reason yet. At last, I would like to highlight our work. So if you want to check out our blog post, we have a blog post written in Notion, which is shown in the right-hand side. Feel free to check it out. We have laid down a lot of model details, our implementation details, also the experiment results there. Also, we have a demo, which is shown in Hugging Face basis. And if you want to check out our source code, feel free to go to our repository. If you like the repository, feel free to hit the star button. Also, we have archived our repository in the papers with code. So lastly, I would like to very briefly highlight our next project. So essentially, what we want to implement next is text to 3D scene. We think that it is a super exciting idea. We see, particularly this year, there is a lot of success in text to 2D image generation. For example, DALL-E and also the DALL-E Mini, which is also one of the projects in the JAX and Flax Community Week. But there's a limited research going on the text to 3D scene generation. So we are asking whether it is feasible. And recently, we do see some evidence that it is feasible. I will try to pick an example that is tweeted by Eric Zhu. Essentially, he wrote a paper which is called Evolving Evocative 2D Views of Generated 3D Objects. And it is featured in NeRF's Creativity and Design Workshop. So in the high level, what he's doing is that to achieve the text to 3D scene, he's coming up with a generator, which is the first component of the system. You have a generator. The generator is essentially a super formula equation. So essentially, super formula equation is an equation which is pretty expressive enough to describe a lot of 3D shape. So once you have these equation, what you can do is you try to tune its parameters. For the super formula, there is 12 parameters. And also, since it is a 3D surface, you need to render it into a 2D snapshot. So you need to determine the viewing pose. To determine the viewing pose, you need 3 additional parameters. So with these 15 parameters, the generator is composed of these 15 parameters. On the other hand, once you have rendered a 2D snapshot, we need a second component, which is a scorer. There are 2 alternatives for this scorer. Firstly, you can use a pre-trained classification model, feed this 2D snapshot into this pre-trained model and evaluate the negative log likelihood of its target class, for example, broccoli. Or as an alternative, you can also use clip to achieve that. Essentially, you are trying to compare the visual 2D snapshot against the caption. The caption is essentially the target class name, for example, the broccoli. And since, as the paper states, that this rendering from 3D surface to 2D snapshot is not differentiable, so he's trying to apply a genetic algorithm to optimize it. What you will end up is some really nice result as you shown here. So this is one piece of evidence showing that text to 3D scene is indeed feasible with the technology that we have. So it gives us confidence that to give it a try. So lastly, we would like to give a big thanks to Google Teams and also Hugging Face for organizing this very nice JAX and Flax Community Week. Without this initiative, I believe this project won't exist. Also, a big thanks to Common Computer for sponsoring us a multi-GPU server. So I think that's all for our presentation.
Awesome. Thanks for the presentation. I think it was great. Before going to the questions, let me quickly share a bit of feedback from the people. Pedro Cuenca says, fantastic job. Congratulations to the team. And I also appreciated that you included a discussion about organization and infra complexities. I think that this project in particular was probably one of the most technically challenging projects from the whole sprint, especially given the timeline. So for the people that don't know, like all of this happened in a timeline of two weeks, maybe at most 3 weeks. And this was like from organizing the team, deciding how to do the project, learning about JAX, having like talks about JAX, Flax, and then training the model, learning how to do it with TPUs, and finally creating a space to demo the project. So it really involved quite a lot of things, and a lot of things to learn in a very short time frame. So I think that it's a great achievement. Like for any team that completed a project, it's already like a huge achievement. And this one in particular, it's very technically challenging. So congratulations on that.
Thank you.
Also, like for the people that want to learn JAX, I think that right now Alex shared some of the resources, and right now it's like a very good moment compared to some months ago to learn about JAX. So from the first sprint, we had some talks, which are already shared. Weights and Biases is also organizing the study group that Alex mentioned. There's like a 27 days of JAX thing kicking off today as well. So there are like many things going on. So I think December, and if you are having like holidays, like Christmas holidays in your countries or something like that, it's like a good moment to learn about JAX. Also, like some feedback from Khalid is that Stella and the team orchestrated the whole project so very well. We don't have that much time, so let me put some of the questions from the people, and let me know if, yeah. So the first question from Kiruka is, how do you get raised? What is the math behind it? I'm not fully sure I understand the question, actually.
Yeah, maybe I guess how we get the lay from the mathematical theory. So it is not that mathematical theory based, just sampling some distribution from the input image. So lay sampling is free or random sampling, and so you consider it.
So maybe I add a few points. So I think for the light ray, you can imagine by the time we try to render a 2D snapshot, essentially like a camera, you're trying to render it in front of the viewer. So what you can do is you can associate each pixel to a light ray, but it is too expensive to consider all the pixels. So usually we will do a coarse sampling. We have a sample rate on it. And once you try to associate a light ray to a pixel, you can do a light ray marching. What it's doing is that from the viewer to this pixel, you march a light ray, and then this pixel will march through this pixel through the 3D scene. And then through the 3D scene, you can start collecting the sample that is along this light ray. So that's how it works. I hope it helps.
Awesome. Thanks for the explanation. George says, congratulations, awesome job. I wonder what your thoughts are on NeRF compared to other image-to-image or bit-to-bit with GAN architectures. Maybe I can comment a bit on this. I think that NeRF is not to generate images, it's to generate 3D objects. So in that sense, it's much more complex compared to usual image data. So that means, for example, if you've played a video game or if you've used Unity 3D or like any game development platform or with virtual reality, you don't have like images, you have like 3D scenes. That means that data is more complicated. You might have meshes, for example, or point clouds, depending on how the data is represented. So in that sense, here you are not generating a new image or a new video, you are generating like a full 3D object. I don't know if you guys have other thoughts on that.
Yeah, you go first, Stella.
Yeah. For GAN, it is normally used in 2D image so far. So NeRF opens some error to generate 3D view dependent model. Yeah, so it main difference is NeRF can generate some 3D view dependent model. NeRF can generate that 3D view dependent model, and GAN make some 2D many 2D generation.
Yeah, to add a few more points. So essentially what NeRF is learning is not an image. What it's learning is a representation of the 3D scene. So what you see is, you can imagine what NeRF is learning is actually a volume. When you try to query a point in this volume, the NeRF will tell you what is the color and the opacity of this point. So with this rich kind of representation, you are trying to, you can use this representation to render different 2D snapshot from whatever angle you want.
Awesome, thanks. Let's go for one last question. And then there were like few other missing questions. So I think it would be great if we can, if you have some time to answer them later on in Discord, and also like share some of the resources that you shared. So let me quickly go to the last one from James Barry. The question is, were any parts of the project difficult when dealing with functions which do not have side effects?
Yeah, Xion, do you want to answer that? But to me, I think because there's no side effect, particularly on the part that you want to JIT or you want to apply the function transformation, it will make the structure pretty unintuitive and pretty different from what you write in PyTorch or TensorFlow. In the way that in TensorFlow or PyTorch, you will have a trainer, you will wrap everything into this trainer, and then you have different associate method. But in some case, this kind of state is not supported in JAX. So in some case, you need to slightly rewrite them.
I know one side effect of JAX. In case of TensorFlow or PyTorch, they can use, I mean, in the distributed learning, PyTorch and TensorFlow can use different batch size for each GPU. For example, GPU1 has 64 images, and GPU2 has maybe 32 images. But in case of JAX, JAX have to distribute the image equally. I mean, because the JAX chart the data using tensor reshape, so it should distribute the image equally for each GPU. I think it is the minor thing, but I think it is the side effect anyway.
Awesome. Okay, thanks guys for this. People were super happy. Yeah, everyone is saying congratulations in the chat. So anyways, thanks everyone for joining. See you in Discord for the remaining questions in the next couple of hours. Feel free to keep asking questions in the next couple of days, and feel free also to follow the team in Twitter. They share like very interesting things, and the next projects will be also quite interesting. So yeah, thanks a lot for joining, and virtual claps, I guess.
And thanks so much for organizing this talk, Omar.
For sure. Thanks a lot.